Hello everybody, I'm Rihab Nish. I'm currently a second-year PhD student at National School of Applied Sciences of Kenitra. Today, I'm delighted to present my work entitled Bitcoin, a lottery every 10 minutes. My presentation is organized as follows. First of all, I'm going to start with an introduction, then I have security services and hash function, then I will define what is a digital wallet and transactions. Moreover, we'll know what is distributed ledger, nonce, and cryptographic puzzle. Also, we have proof of work, proof of stake, and forks. And in the last part of this presentation, I will answer to important questions related to the Bitcoin. And finally, to recap, we have a conclusion. From its inception as a Bitcoin platform by Satoshi Nakamoto in 2009, blockchain has evolved into an all-encompassing revolutionary backbone technology that brings value to organizations across industries. However, the most successful blockchain implementation to date is Bitcoin, the peer-to-peer electronic cash system. First of all, I'm going to start my presentation with security services. So, what are a security service? A security service is a service that enhances the security of data processing systems and information transfers. On the other hand, we should also define what is a security mechanism. It is a mechanism that is designed to detect, prevent, or recover from a security attack. Here, in this following schema, it highlights the security mechanisms used to achieve these following security services, like privacy, which stands for the information is only available to the people intended to use it or see it. Also, we have integrity, which is the information is changed only in appropriate ways by the people authorized to change it. Also, we have authentication, means a person's identity is determined before access is granted. Moreover, we have non-repudiation. It means a person cannot perform an action and later deny it. And finally, we have availability, which stands apps and services are ready when needed and perform correctly. And each one of these security services require a certain security mechanisms like encryption, which is divided into two types like public key and symmetric encryption. Also, we have hash, digital signature, and distribution. After we defined what is a security service, now it's the turn for security mechanisms. In this slide, we're going to dig deeper into security mechanisms, which are encryption, hashing, and digital signature. So, public key and symmetric encryption are two types of encryption. Let's start with public key. A public key, also known as asymmetric, it is a form of crypto system in which encryption and decryption are performed using different keys. Public key known to everyone, and another key, which is a private key, it's kept secret. And privacy can be achieved using public key encryption, where the plain text is encrypted using receiver public key. This will ensure that no one other than receiver private key can decrypt the ciphertext. On the other hand, we have symmetric encryption. It is a type of encryption where only one key is required. In simple terms, the sender encrypts data using a password, and the recipient must know that the password to access the data. Now we move to hashing. Hashing is a method of cryptography that converts any form of data into a unique string of text. It means a hash is designed to act as a one-way function. It is a mathematical operation that is easy to perform but hard to reverse. And finally, we have digital signature. Digital signature, it is a mathematical technique used to validate the authenticity and integrity of a message, software, or digital document. Also, a digital signature is intended to solve the problem of tampering in digital communications. Also, digital signatures can provide evidence of origin, identity, and status of electronic documents, transactions, or digital messages. The individual who creates the digital signature uses a private key to encrypt signature-related data, while the only way to decrypt the data is with the signer's public key. Now we move to hash functions. A hashing function is an irreversible cryptographic function that takes in an input and produces a unique, fixed size and compressed numerical value called a message digest. Talking about a message digest, it is a fixed size numeric representation of the content of a message, computed by a hash function. Also, a message digest can be encrypted forming a digital signature. As we can see in the representation below, we have a plain text, and after applying hash function, we obtain a hashed value. And now we move to classes of cryptographic hash functions. There are several different classes of hash functions. Here are some of the mostly commonly used. We have secure hashing algorithm, SHA-2 and SHA-3. We have race integrity primitives evaluation message digests, and we have also message digest algorithm 5, and we have Blake 2. We cannot talk about a hash function without mentioning its properties. There are 6 major properties of hash function. First one, irreversible. It means that it's possible to go from the input to the output, but it's impossible to go through the opposite way. Second property is deterministic. It means for a single input we will get always the same output no matter what. The third property is collision resistant. It means that it's impossible to have the same output digest for 2 different inputs. For the fourth property, we have a large output space. It means the only way to find a hash collision is via a brute force search, trial and error. Here I should mention the avalanche effect. What is the avalanche effect? It means if a slight change happens in the key or the plain text in the hash will change drastically. And we have pre-image resistance. It means that it is infeasible to determine the input of the data based on the output hash. Notice I used the word of infeasible instead of impossible, because if we take a small example, let's say a numbers between 1 and 5, and we compare the hash we had, we will obtain surely a correspondent hash of the number, and we have the number exact in the first step. But in the case of a huge amount of data sets, it's infeasible and impossible to find the input plain text. And lastly, we have fast computation. Hash functions are fast and efficient because they rely heavily on bitwise operations that are easily processed. Now I'll move to the digital wallets. Digital wallets. Crypto wallet, it is a device or program that allows users to exchange funds easily and manage different kinds of cryptocurrencies. Transactions are secure as they are cryptographically signed. There are different types of crypto wallets, such as paper wallets, hardware wallets, and software wallets. Private and public keys. It is important to mention them when we talk about a wallet. When we start into cryptocurrency, we are assigned a private key, and that is like our unique secret identifier. And then from this private key, we can generate a public key. In the case of cryptocurrency, a public key is what we need to share with others for them to send us cryptocurrencies such as Bitcoin or Ethereum or any kind of currency. And here we have a message. In our case, let's call it a transaction. So the question here is, how can we use private and public keys to secure this message? Well, the private key is combined with the message, and together they can generate a signature. This signature will always go with this message. Another question here is, how can they verify who signed this signature, who made this signature? Well, that's where the public key comes in. In exchange, there is a verification function in the algorithm where anybody who has the message, signature, and public key, these 3 components, they can put them into the verification function and it will spit out a yes or no. that this message was signed by this private key, and indeed this transaction was initially made by the person who holds this private key. Now I'll move to the public address. I kept the same diagram but with some modifications. A public address is obtained from the public key by applying the hash function 256. It is also known as the address where we can ask people to send us currency, as just with the public key. It is something that we don't have to keep private, it is shared publicly. But what is the point of using this address while we have already a public key? So the reason is we want to keep the public key unexposed too often. We definitely will have to expose it because we cannot run the verification function, and also the people cannot confirm that the transaction is valid or not. So we will have to expose the public key but when we send the currency. But when we receive currency, we have the choice to avoid exposing it. Another trivial question here is why we should avoid exposing the public key as much as we can. Well, the reason behind this is this additional layer of protection, which is composed from the public address by using the hash function 256, enhances the security of the public key. Another important term in blockchain is transactions. So let's see what it is. Transaction on the Bitcoin blockchain consists of cryptographically signed inputs, what was sent, and outputs, what was received. On the other hand, a UTXO or unspent transaction output is like a bank check. It is a guaranteed form of payment that has an origin, the sender, a destination, the receiver, and the contents or value. The following picture represents a blockchain, where each block contains multiple transactions. Here I have an example of transactions. The following list represents the people who sent me bitcoins. These values represent also my UTXOs, or in other words, my unspent transaction outputs. Let's say that I want to buy a car for 0.9 BTC and a bike for 0.02 BTC. So what I need to do here, I need to pick the highest value in my following list, which is the value sent by Manan, then the value sent by Mark, and finally the value sent by Sarah. These values gives me as total 1 BTC, so I will put them as inputs to my transaction. And for the outputs, I get 0.9 to the bookshop goes as UTXO to the bookshop, 0.02 goes to the fruit shop, and the last value goes as UTXO to myself. But actually we have another value, which is the fees for the miner. These values goes as UTXO for the miner and are calculated using this formula, inputs minus outputs. Here we have another question, why these fees are important. So, well, the higher amount of transaction fees, the rapidly the transaction is processed by the miners. After defining what is a transaction and what is a UTXO, now is the turn for transactions pool. A transaction pool is the place where contains all of unconfirmed transactions. Transaction pool also is stored on a special device and its content can be accessed, observed in real time. So when we sign a transaction, we send it. Then it becomes an unconfirmed transaction. This unconfirmed transaction is added to a pool called a pool of transactions. Then the miners from this pool of transactions choose the next unconfirmed transaction to add it to a new block based on the transaction fees. So after they pick the one they want, it is added to a new block, and this block is added to the whole chain, and the same thing goes for the next blocks, the next transactions. It is a database that exists across several locations or among multiple participants. It is used to eliminate the need for a central authority to process, validate, or authenticate transactions. It is immutable, secure, anonymous or pseudonymous, transparent, programmable, consistent, and finally time-stamped. Now we move to blocks and chain. A blockchain is a form of public ledger, which is a series or chain of blocks on which transaction details are recorded after suitable authentication and verification by the specified network participants. So here we have the Genesis block, contains data, previous hash, and hash. Here we can see that the previous hash is zeros because this is the first block. It is connected to another block with the same thing, data, previous hash, and hash. Also, we have a third block with the same thing, data, previous hash, and hash. We can observe that the previous hash of the second block is the hash of the Genesis block. Same thing goes for the third block. The previous hash of the third block is the hash of the second block. We can conclude that the blocks are cryptographically linked together. Then the same thing goes for the rest of the chain. Another backbone of blockchain is the nonce, or number used only once. Nonce refers to the first number a blockchain miner needs to discover before solving for a block in the blockchain. The world of crypto mining is challenging, and one often needs excellent computational power to even begin to try and solve the nonce. So here we have a block, and we have inside block ID, or the number of the block, we have the data contained, we have the previous hash, and obviously the hash. So we cannot change the data number, the block number, we cannot change the data because blockchain is known immutable. If we tamper the data, so we break the rule of the blockchain. We cannot change the previous hash because the blocks are cryptographically linked. So the only thing that we can change to change the hash to obtain a next or the following block is something we call the nonce. It is located here. So the miners, what they do, they change the nonce until they find the right hash. We'll see more details in the next slide. Here we'll detail more the nonce and what the miners do. So let's say we want to have a hash that starts with 40. This is our target. So the miners need to find a nonce that corresponds to this hash. So they start by putting numbers. Let's see for this first number. Then a hash is generated. From this hash we can observe it doesn't match what we want, so it is eliminated. Then we have another nonce, 23. We'll see what will generate. Another hash doesn't match what we want, so it is also eliminated. Then another nonce, 64. The hash is generated. The same thing, it doesn't match what we want. Then another number is here. The hash is generated. The same thing, it doesn't match what we want. It is inconvenient. So here we have another number, and the hash is generated. We can see that it starts with 4 zeros. So the miners, they are the winners, and they obtain a golden nonce. And they can add the next block of the chain. And the same operation goes for all the chain. Bitcoin is based on proof of work. It is a consensus mechanism. Also, it is a form of adding new blocks of transactions to a cryptocurrency's blockchain, where crypto miners compete with each other to win the right hash to update the blockchain and then receive rewards. So here we have an explanation of proof of work. The network server sends a puzzle to the miners. Then the miners here try to solve this puzzle. They compete with each other to find the right solution. Then they send their solutions to the network server. After that, the network server checks the solutions. In this case, the first miner is the winner. So he receives the rewards and he would be able to add the block. And this becomes the new blockchain. Another consensus mechanism is proof of stake. Proof of stake, it is a type of consensus mechanism used to validate cryptocurrency transactions. With these systems, owners of the cryptocurrency can stake their coins, which gives them the right to check new blocks of transactions and add them to the blockchain. Now let's see the major differences between proof of stake and proof of work. So let's start with proof of work. In proof of work, mining capacity depends on the computational power. On the other hand, in proof of stake, validating capacity depends on the stake in the network. Also, in proof of work, miners receive block rewards to solve a cryptographic puzzle. On the other hand, in proof of stake, validators don't receive a block reward. Instead, they collect transaction fees as a reward. Finally, in proof of work, hackers would need to have a computer powerful than 51% of the network to add a malicious block, leading to the 51% attack. While on proof of stake, hackers would need to own 51% of all the cryptocurrency on the network, which is practically impossible, and therefore making 51% attack impossible also. We'll see more details about 51% attack in the next slide. Another term in the jargon of blockchain is forks. Well, to be able to produce blocks, miners must reach a consensus regarding the blockchain state. Once participants of the network fail at reaching the consensus, a fork can be proposed as a solution that will resolve the conflict. A fork happens for several reasons. These are the major ones. The first case when a fork happens when there is no consensus between participants of a network. Another case when forks happens when a blockchain requires critical updates. So forks are divided into two types, soft forks and hard forks. The first case when fork happens is when there are two nodes are able to add a block at the same time. So the longest chain is the chain of blocks that took the most effort to build. Nodes always follow the longest chain to accept it as the valid version of the blockchain. So here we have more details. Let's say that we have node A, node B, and node C. They are connected with each other. And let's suppose that node A and node B were able to add blocks at the same time. So what happens here? So node C, here when we call a fork, chain splits. So after that, let's suppose that node A were able to add a next block. So this is the longest chain, and the block added by node, it becomes an orphan block. Node C remove this block. This is the newest valid version of blockchain. A soft fork, it is an update of cryptocurrency protocol software to improve the work of a particular blockchain, where the community together with developers decides to improve the software of the network. Well, here we have an explanation what is a soft fork. So let's say that we want to resize a block from 2 megabytes to 1 megabyte. So this is the new rules. We have already a blockchain which is composed with blocks of 2 megabytes. So here a soft fork is implemented, then a new block is created with the new rules. Another block in the old blockchain also is created. So here we have another block added to the new chain. The same thing goes for the oldest chain, but we can observe that this time a block is added with the oldest rules. So the block breaks the new rules, and then this oldest chain is no longer valid in our blockchain. Another block is added, then here the consensus is reached, and here we have the continuity of the blockchain. So what is a hard fork? A hard fork happens when there is a change in the software codes of the original blockchain protocol in the pursuit of enhancing its features. So let's say that we have a normal blockchain that contains transactions, and here we have the continuity of this chain that follows the old rules. So when a hard fork is implemented, the chain splits and a new blockchain is created that follows the new rules. So the blue ones are the blocks from non-upgraded nodes, and the green blocks are upgraded nodes. In a hard fork, non-upgraded nodes reject the new rules and therefore the chain splits. In the last part of this presentation, I will answer what is the block generation time, why there is only 21 million bitcoins, and what is the 51% attack. Another trivial question related to the Bitcoin is why it takes the network around 10 minutes to add a new block. Well, in a Bitcoin, a new block is created every 10 minutes. In other words, what determines the 10-minute generation time in Bitcoin is the target. We can say that the target number is the pacemaker that keeps Bitcoin ticking with one new block per 10 minutes. In other words, by adjusting the target up or down, we change how quickly miners can create a new block. A high target means blocks created quickly. A low target or more leading zeros, miners take longer to find the solution to create new blocks. The difficulty of mathematical problem is automatically adjusted every 2016 blocks around 2 weeks to solve the cryptographic puzzle. It depends on the computational power on the network. That's why we said a Bitcoin is a lottery every 10 minutes. So after we explained why a block in Bitcoin takes 10 minutes to be created, so let's see now what is the difficulty. The current difficulty target is 19 leading zeros in hexadecimal or 76 bits. The probability P to have this event is 1 divided by 2 raised to 76. And the following formula gives the number of trials needed to meet the difficulty criteria with confidence P. If we want to obtain a hash value with 76 leading zeros bits with 90% probability, we need this number of trials. That means 5 trillion years of work for an i7 core-based desktop. Another important question here is why there are only 21 million bitcoins to mine. Well, before we start, we should mention that there are 100,000 bitcoin miners. They compete to get the reward. This reward is halved every 4 years or around 210,000 blocks. At the start of the history of a blockchain, and especially the Bitcoin, the reward was 50. Then this reward was halved into 25. Then the reward was halved into 12.5, and currently the reward is 6.25. The 21 million bitcoins originate from the following calculation. Mining all the 21 million bitcoins is predicted to happen in 201,040. One of the most popular attacks in blockchain is the 51% attack. It describes a situation where a certain miner or mining pool that owns more than 50% of all the network's hashing power acts maliciously to disturb the network's operation. So here we have an example. The truthful miners are adding blocks to the public chain by broadcasting them. On the other hand, an attacker is adding blocks to a private blockchain and not broadcasting them to the public blockchain. So, a miner employing a 51% attack will be able to double spend in his coins and second, prevent transactions from being confirmed, while he would not be able to reverse confirm transactions, create false transactions that never occurred, steal funds from a certain address, and finally create new coins. So here we have a demonstration of what's happening inside the real blockchain, specifically the Bitcoin. So here we have this website called Blockchain Explorer. We can check it also. It is a website that shows the real blockchain and what's happening inside a real blockchain. So here we have the meme-sized prices. We have also the latest blocks added, the latest transactions added. So for example here the latest block is added 7 minutes ago, and here we can see that transactions are updated. So let's take for example this block, the latest block added here, and we can see a lot of information inside the block. First of all, the block number, the hash of the block, the confirmation, the timestamp when it was added, the miner, in this case it is unknown, the difficulty, Merkle roots, other important information. And the months that we talked about, transaction volume, a block reward. Here is, we said that currently in 2022, the reward is halved into 6.25 BTC. And the fee reward, and we can also find the block transactions included in this block, the fee, the hash, and supplementary information. To sum up, Bitcoin known as the first successful blockchain implementation. Currently, the world has discovered blockchain technology applications in a variety of industries far from monetary uses, where confidence is required without the participation of a centralized authority. So Bitcoin is just the beginning of a new revolution in the world of technology.